We're going to have another session. We're going to have 3 presentations. First is from Jeff Adie from NVIDIA Corporation. So I will introduce Jeff and then he's going to present his part. So Jeff is a HPC specialist with over 30 years of experience in developing and optimizing scientific cores and architecture HPC solutions. Jeff leads the Earth System Science Research Team for the NVIDIA AI Technology Center's joint laboratory established at NTU in Singapore. Then he works on collaboration with industry partners and academia in the field of accelerated climate, weather research, and in application of AI to Earth system modeling. Jeff holds a postgraduate diploma in computer science from the University of Auckland, and interestingly, he's currently pursuing PhD from University of Newcastle on time. So I welcome Jeff. So over to you, Jeff, for the presentation. Yeah.
Okay, we all online? Okay, can you guys hear me?
All good. Please continue.
All good? Okay, great. Thanks. Okay, hi everybody. Yes, I'm Jeff Adie. I work at AI Technology Center, which is a joint lab with one of the local universities here in Singapore. And today I'm going to talk a little bit about how sustainability is really important to the work that we do in our research in climate and weather. So let me just, it's my rough agenda that I want to talk about. So I'm going to talk a little bit about a quick introduction and then talk about some of the challenges we have in our climate models that we build and some of the ongoing sustainability issues. And a lot of these are related to computability, the cost of computation, and energy consumption in building those models. And then I want to talk about some of the solutions that we're looking at in using artificial intelligence to improve the sustainability of our climate and weather models. Okay, so a very quick introduction to my team. As I said, I work in the NVIDIA AI Technology Center, where I lead up all of our Earth system science research. NVAITC was established in 2015 to provide a mechanism for collaborative research between NVIDIA and researchers in academia, government, and industry. In the last 5 years, we've grown from a single lab in Singapore to over 24 joint labs around the world. I work in the original joint lab, which was based at Nanyang Technological University in Singapore. And my group has done over 50 research projects in climate and weather space. We do a lot of different types of projects. We do work in numerical simulation. We work in AI models, AI surrogate models, and hybrid approaches that combine both numerical simulation and AI together. We do projects in a wide variety of fields to look at various aspects of both weather forecasting right through down to nowcasting, all the way out to full climate model runs. Our research collaborations are international, so we don't just work in Singapore. I work on collaborations all around the world. So let's start with a problem statement. Climate change is fundamentally affecting the future state of our planet because of the additional energy that's being captured in the system, and it's driving more and more extreme weather across the globe. It's pick a disaster. Every day there's a new one. We've just had some flooding in Afghanistan very recently. But we're seeing more and more of this extreme weather that's being caused through climate change. We know that modern climate models are our best tools for predicting climate change at global scales. But what's becoming increasingly clear is our tools aren't good enough. The words that I hear all the time when I talk to climate scientists, and often you'll hear them if they're interviewed on the TV or whatever, is they'll talk about things that are astonishing or amazing or unprecedented. They're using this type of terminology because our climate is changing much faster than we expected. So our models are not giving us the right amount of data. And it's really important that we have those capabilities to prepare for our future that we're going to have. In Singapore, for example, rising sea levels is our #1 problem. A third of our country is less than 5 meters above sea level. And that's a big problem when you live right near the equator. We have heavy monsoonal rains, and that water has got nowhere to go. So flooding becomes a major concern for us. The second point is, the first point is that rate of climate change is happening a lot faster than our models are predicting. The second thing to keep in mind is that our future climate is going to be very different to what we've had in the past. So our historical values, let me just put my laser pointer on here. We're very different. This is a chart here of global surface temperature. Okay, and so we can see the global surface temperatures as they change throughout the year. We get the hottest temperatures in the northern hemisphere in June and July, of course, during summer. This orange line here is 2023. And for 2/3 of the year, we broke temperature records for global surface temperature. The black line here is 2024. So that's where we are today in May. So we can see that these are just getting higher and higher and meeting more and more extreme values. If we look down here at what we call our climate stripes, we're currently about here. This goes back about 150 years. And what's important to note is that if we look at our future pathways, these are what we call SSPs or shared socioeconomics pathways, depending on what we do to react to climate change, so like the do nothing approach or reducing our carbon emissions and so forth, whatever we do doesn't take us back to the past that we had. So we know that our future state is going to be different to our past state. Okay, we have thermal inertia baked into the system for a long period of time. And the net effect of all that increased energy in the system is, of course, an increase in the frequency and the severity of extreme weather events. Okay, we're seeing these events occur at different times of the year in different places than they historically have, and at different levels of intensity. Here's just some examples here. So we had some terrible heat waves in the Mediterranean last year. Hurricane Ian did over $100 billion worth of damage, 112 billion in fact. There were terrible Pakistan floods where they had severe droughts and then massive flooding events, one after the other. And so these are all causing huge losses of damage to both life and to property. Last year in Thailand, so I live about here, just down under Malaysia. We saw extreme record temperatures. We had just had a large Southeastern Asian heat wave this year as well, but I don't have the data for this year. In fact, it got so bad that the plan that the government came up with was that we should kidnap Elsa from Frozen and bring her to Thailand to try and bring the temperature down. And what we've found is that, if we look at the World Economic Forum, their global risk report for 2024, we can see the #1 risk that economists are seeing is extreme weather events. It even outranks things like AI-generated misinformation and disinformation. And interestingly, if you look over the last 2 years or even over the last 10 years, all of these items in green represent environmental concerns, if you like. So in the last 10 years, the top 4 have been extreme weather events, critical changes to Earth systems, biodiversity loss, and natural resource shortages. So these risks are very, very important. So in understanding those, what we do is we build these models, okay? And there are a lot of challenges in the models that we had. As I said in my introduction, one of the big problems we have is that our models are not good enough. We know that they're not good enough. And the main reason for that is that predictions today are too low a fidelity. Our resolution of our models is too low. So basically, we have to solve a set of partial differential equations that are discretized across a globe that represents the Earth. And we have computational limits on how fine the resolution of that mesh can be. And if we look at a typical climate model today, each of the squares that we model is approximately about 100 kilometers on a side. And that gives us poor resolution to understand what's happening at the local level. So we have to take that coarse output from our climate models and then downscale it, if you like, to super resolution it to have a regional model that we can use. This is important because decisions on how to tackle climate change are made at local levels. Climate change is a global problem, but tackling it is a local problem. It's up to local governments and countries as to how they deal with that. The other big problem is that the largest cause of uncertainty in our future predictions is in clouds. So understanding cloud feedbacks and how clouds are going to be in the future is really, really important. So clouds primarily affect the amount of solar energy that the Earth receives. We know if we improve our resolution, we get more accurate predictions. And that's all great. That's where we all want to be. The problem is we're about here today, okay, where globally we can run at about 25 kilometer scales. Okay, we'd like to get our climate models up to about 1 kilometer at least, and ideally down to about 100 meter in resolution. The problem is to get to from where we are today to where we want to be, we need about 30,000 times the amount of compute power that we have currently available. And to get to a high resolution fidelity, we're looking at something like 500 million times the amount of current computational capabilities. We don't think we'll get there looking at how computing hardware is evolving until about 2060. And we can't really wait that long for our climate models. And the problem is that fidelity isn't the only problem. It's really only one axis of the computational requirements we want. We also need to improve the science in our models as well. So over the decades since the 1960s, we've added more and more processes into our climate models to make them more realistic. So we've included things like the carbon cycle, ice sheets, and put more and more science into our models, but of course that makes them more and more complicated. We also want to run lots of different scenarios. We want to see what happens if you double the amount of carbon in the atmosphere, what happens if you take half it out, and so on and so forth. So we run all these different models, these different scenarios. We also want to do probabilistic distributions of those models as well. So we don't just run them one time, we want to run them several times. We run them with slightly different initial conditions. That gives us a probabilistic spread, which helps us to understand uncertainty in our models. Because with a range of models, we can then select a mean and get a variance. So all of these things add to the cost of running our climate models. And this leads us to the sustainability issues. So the good news is that our computers keep getting bigger. So just earlier this week we have the International Supercomputing Conference currently going on in Hamburg. So twice a year, the supercomputing community gets together and they release what's called the top 500, which is a list of the 500 biggest supercomputers on the planet.
Yeah, but I have not finished making my slide.
So this is the list that was released on Monday, showing the top 500 supercomputers. I've just listed 5 of them here. What's scary, these are marvelous machines and they're absolutely enormous. But if you look at the amount of power that these computers require, okay, so we're looking at something like 22 megawatts for the largest supercomputer on the planet, but nearly 40 megawatts for the second largest one. And again, even the fourth largest one is around 30 megawatts. So these are very, very large computers that use a very large amount of energy. That's a big problem because going forward, we are looking at more and more larger supercomputers and more larger data centers. So there was a couple of months ago, there was this report that Microsoft and OpenAI, of course, OpenAI are the people who created ChatGPT, are partnering up for a $100 billion data center. That data center will use 5 gigawatts of energy. Okay, so it's 5,000 megawatts of power that will require. And then just last month, just last week, there was this report out that there's only about 2 gigawatts of spare energy left in the US energy grid. So powering a 5 gigawatt data center or adding that to something that only has a 2 gigawatt capacity is a bit of a problem. And there are people seriously looking at putting small modular nuclear reactors into some of these new data centers that are going to be built out in the future. So that's a really big thing. As far as energy efficiency goes, one of the good things that's come out of the hardware is it turns out that GPUs lead the way for energy efficiency. Okay. Fundamentally, GPUs process data differently to CPUs. In CPUs, you tend to have a small number of cores that run at a very fast speed. They have a high clock rate, whereas GPUs have a much higher number of cores that run at a slower clock rate. Because energy is a cube of the frequency, it turns out that GPUs are a lot more energy efficient. And so as well as listing the 500 biggest supercomputers in the world, they also list the 500 greenest supercomputers in the world. So this list, called the Green 500, was also released on Monday. And that shows the energy efficiency of each of these systems. And what's interesting on this one, and I thought you guys might find interesting, is that at the University of Bristol now holds the second most energy efficient supercomputer in the world. And this is Isambard AI phase 1, which is shown in the bottom right there. It's something like 68 gigaflops per watt. So that's a really impressive feat that we've seen in the UK. In fact, you have to go 65 places down the list to find a system that isn't using GPUs for its energy efficiency. That's great, and there's been some studies on using GPUs to help with our climate models. The Department of Energy in the US, through the National Center of Atmospheric Research, put out a report a couple of years back showing how they could reduce the carbon footprint of their weather models using GPUs. And last year, my lab put a paper out in IEEE on reducing the carbon footprint of ensemble weather forecasting using GPUs. So there's been some studies being done on that. We do get this thing called climate shaming, where people talk about the energy that we're using to model how much energy we shouldn't be using, and that's a problem. Our climate models tend to need very long runs on very large supercomputers. Okay, just to give you a taste for it, this box here on the bottom left is the data from a study that was done at Meteo Swiss, at the Swiss Supercomputing Center, where they looked at what it would cost to run a global climate model at a roughly 1 kilometer resolution. And they found it would take 840 days, so a little over 2 years, to run a 40-year simulation. It would require 22 gigawatt hours of energy, which would cost roughly $1 million US. It would generate 3,800 tons of CO2. And if you did it on a system like on AWS or Google, it would cost you around $68 million just for the node hours. So obviously doing this is completely unsustainable. This is where we want to get to. We want to get to the sort of 1 kilometer magic resolution. But at these costs of doing it is completely unsustainable using today's technology. So can we use AI to improve the sustainability of running our climate models? And the answer, of course, is yes, otherwise I wouldn't be here. But that's primarily what we've been doing in my lab. And I'm going to go through 4 applications where we've used AI. to improve the sustainability of our models. And the first one is this idea of building what we call surrogate models or AI emulators. And the basic idea is that we can teach an AI model, a neural network, a function. And a function that's computationally expensive, that uses a lot of energy to compute, I can replace that with a pre-trained model that can run that function very quickly. That's the basic idea. You can kind of think about it if you were like pre-computing all the possible values of something and putting that all in a table. Okay, so then at runtime, all you have to do is look up the value in the table, and that's very fast. It doesn't require a lot of heavy compute to do that. So that's the basic idea. Here's an example of actually using it. So this is a collaboration that we have with Newcastle University. This is actually part of my doctoral research, where we're using an AI emulation model for what's known as the chemical transport mechanism. So when you're studying the makeup of the atmosphere, all the different chemicals are in there, there's about 300 chemical species that we care about. We have to model all of those. We have to model them using this thing called a chemical transport mechanism, which has, how does the chemical move from one place to another? So we have emission, we have deposition, we have advection, where it's being moved around by the winds. And as well as that, we have chemical reactions that are occurring. So there are productions of some of the chemicals and losses of some of the others as they turn from one species into another. And all that depends on temperature and pressure and presence of water and all kinds of things like that. So it becomes enormously complicated. So there's roughly sort of 3 reactions per chemical species and roughly 300 chemical species. And you have to do that for every grid point on the planet at every time. That's incredibly expensive to do. It's so expensive that, in fact, most climate models today don't do atmospheric chemistry studies at all. It's just too expensive. But what we've found is that by using a surrogate model of this, right, we can run it at about 1,000 times faster, but we can also save nearly 600 times the amount of energy that it would take to run that computation. So it's faster and it uses a lot less energy. And that's really important. Moving on from emulation is the idea of data-driven models. And this is this idea that rather than having a complex numerical model that has lots and lots of calculations that need to be done, we can learn stuff from the data. The data has skill in the data itself. So we can take terabytes of data in or petabytes of data, and we can effectively replace millions of lines of code in order to do that. Again, another example, this is with collaboration between my lab and Coventry University, where we studied what would happen if we planted a bunch of mangroves in the Bangladesh river delta. So Bangladesh is effectively the whole country's a river delta where there are 3 major rivers that come together leading up to the ocean. Because of that, they also get a lot of tropical cyclones, and so they get a lot of flooding. And so what we were looking at was what's the impact on those tropical cyclones if we plant a whole bunch of trees. And this is extremely computationally expensive to try and figure out. And so by using a technique called physics-informed neural networks, which is where we use a data-driven approach, but we apply physical constraints to the data itself, we were able to get a 3 orders of magnitude improvement in the numerical model. We can then go like, just forget about the physics altogether. Let's just look at the data and nothing else. And you get this idea of what's now known as AI weather prediction models. Okay, where we do a full model emulation of, say, a weather model itself. So there's no computational component whatsoever. And the first time that this was done at a global scale was really a model called ForecastNet that was developed by NVIDIA in February 2022 as a global medium range weather model that worked at a global 25-kilometer resolution. Is trained on 36 years of data, okay, and it runs about 10,000 times faster than actually doing a numerical simulation itself, and also saves about 4 orders of magnitude in power as well. And that's really, really important. So ForecastNet was the first model that could actually work at a usable resolution. So there've been lots of approaches before, from 2018 onwards, with various different types of AI approaches, from multi-level perceptrons to convolutional neural networks, to convolutional LSTM networks, residual networks, graph neural networks, and then ForecastNet applied transformers. And transformers, of course, are what you get in your it's the T in GPT from ChatGPT, and these allowed us to basically work in parallel, and that made it the capability of being able to work in full resolution possible. And what these models do, because they do full model emulation and it's really fast, it becomes extremely power efficient. I can do a 10-day weather forecast in a quarter of a second. Okay, effectively in a power consumption, that's free. Okay, I'm effectively using no power at all to do that, as opposed to using several kilowatts to do it in a normal way. And that leads us to new capabilities as well, because now we can afford to run lots and lots of forecasts because they're effectively free. And then we can do things that we couldn't do before. We can produce enormous forecast ensembles where we have thousands and thousands of weather forecasts, and we can compare them. And here's just a quick example here, looking at some wind speeds over Miami. If we could run 50 forecasts, and numerically that's about the limit today, on a $100 million supercomputer, you can run around 50 weather forecasts in a reasonable period of time. And we can see the results that, if we bin these into different wind speeds, get a rough idea as to what the potential wind speed is going to be in the forecast. But if we can add a lot more forecasts by doing them effectively for free, we can now afford to run like 1,000 forecasts. Now we get a much higher distribution of our data. Okay, we start to resolve the tail of the distribution, which allows us to predict, potentially rare but very damaging high wind speeds. And so this is some of the value that these models have come from. Okay, and the nice thing is that this has produced a whole bunch of research into this idea of what we call AIWP, or AI-based weather prediction. And so while ForecastNet was the very first paper to do this, there's been several others that have come out since that time that take advantage of these capabilities. And the final thing I wanted to talk about was this new thing that we've had in the last year or so. It's not new, okay? We've been doing generative AI for probably about a decade or so, but it's become very popular in the last 12 months. And so a lot of people talk about these Gen AI models where they can actually generate content directly from prompts. And this gets really interesting because one of the problems with our global models today is their resolution is too coarse. So can we use things like generative residual diffusion models to downscale our global data down to our fine regional data that we want? And this is largely what we were trying to do. So this is a paper we just released last October on a technique called CordiF, where we use a stochastic differential equation denoising algorithm to calculate high resolution data from coarse resolution. What's exciting about this is it gives us the capability to do regional forecasting at kilometer scales without actually having to do it numerically. So taking the fact that we can now do these global models effectively for free, now we can start looking at doing regional models. This is 500 times faster than having to calculate it using a numerical model, and it's 210 times more energy efficient. And all of these energy efficiencies make it possible for us to run these models on our supercomputers without blowing our energy budgets. So I think that's probably the most important thing that comes out of our research at the moment. So in summary, modeling our planet to look at climate and weather is a really difficult problem. Our planet is really complex. There's lots of complex processes that go on that we need to deal with in our science. And we know that we need to improve our accuracy of our climate models. Okay, we've really been caught out in the last few years with how quickly our climate is changing, and it's doing things that we didn't expect from looking at our climate models. So we need to get our climate models better and better and better. But the cost of doing that is not sustainable today. So AI is a really important tool that we can use to accelerate these models so that they use less energy, they take less time to run on the computers. So this becomes a sustainable way for us to do our future climate models at the fidelity and the scientific value that we require. And I think that's probably where I'll stop. Thank you very much, and very happy to take any questions.
Thanks, Jeff, for interesting presentation. Time for questions. Yeah.
Hello, Jeff.
Hi.
My name is Eric. By the way, I'm a colleague of Simon C. I was the PI of the NVIDIA AI joint lab in Brazil. Then I'm here in the UK right now working at the University of Surrey. So a pleasure to meet you at this time in a two-dimensional way. Thank you so much for your presentation, very insightful. I have been working a lot with atmospheric science modeling using numerical models, semi-analytical models, and also deep learning AI models. So I have 3 questions for you, if you can please elaborate on them. So, for example, you showed about your wonderful work on chemical transport models and the developing of AI surrogate models to do the work of numerical models in this regard. So what did you use? Did you use physics-informed neural networks or data-driven approaches or a mix of them? This is the first question. The second question is, are you familiar with the concept or the very recent work that some people are doing in the area of foundation model for weather forecasting? I've been working with it. And for example, Microsoft has just launched, actually 1 year ago, they launched the Climax, the first foundation model for weather forecasting using Era 5 data. So this is the second question. And the third question is, for this work that you just mentioned about the diffusion model that you developed, did you use WRF output to train this model, to do the downscaling, to train your diffusion model using WRF output in a finer grid resolution or something else? And thank you so much once again.
Okay, let me try and remember all 3 questions.
I can remember you if you want.
So the last one first, because that's probably easiest. So the residual diffusion downscaling model we built was indeed, we used WRF as our high resolution training samples. So we're using 2-kilometer WRF models that were built over Taiwan. This was in conjunction with the Central Weather Agency in Taiwan.
Great, wonderful. And the other question was about, well,
foundation models. Yes, I remember that one.
Models, yes.
Yes, so I'm quite familiar with Climax, and the more recent work that's been done with Microsoft and Argonne National Labs on Stormer. The other one that's quite interesting is AtmoRep that comes out of CERN as a foundation model. So I think we'll see more and more of them. It's a little bit disingenuous to call some of these foundation models because the implication there is that it'll work in all scenarios, and in practice that's not quite how they work. Yeah, the idea of a foundation model is that you can take it and then you just sort of need to tweak it for your region. But they are improving. There's certainly no doubt about it. There's no doubt Stormer is a major improvement over where Climax began.
Great. And the first question was about how did you build your AI surrogate model for chemical transport modeling?
Yeah. Yeah, so the CTM model is a classic AI surrogate. So it's simply it's trained on data from GeosChem, which is a sort of standard numerical atmospheric
Yes, I
chemistry
know.
model. We train it in situ, so we use there's a Fortran to Python interface that basically replaces the solver step inside GeosChem with a pre-trained neural network model.
Yeah, wonderful, Jeff. Thank you so much, and looking forward to collaborate with you and in further collaboration in the future. Thank you.
Well, thank you so much for such a detailed and clear presentation on very complex areas for somebody who is not a modeler, climate modeler, or an AI specialist. So I'm Dr. Fiera Leśniewska. I'm at the University of Surrey, and I'm a sustainable transitions environmental law academic. So my question is, because we rely a great deal on modeling from climate scientists to develop law and policy, when you're the various alternative approaches that you presented, what are the degrees of inaccuracies that are baked into them, and how do you communicate that when you're presenting a model there is a degree of potential inaccuracy? Because obviously you said at the very beginning we've had climate models that are no longer really fit for purpose. So what you're presenting now, how good is it for doing the job of adaptive law and policy for climate change?
Sure. So largely what's been missing from the older models is that because the size of the models, the resolution of the models, if you like, isn't that good, they're quite coarse, they don't capture what we call subgrid scale processes very well. So they basically have to come up with a value for each grid point. And that grid point may represent, 10,000 square kilometers of land, which can have all kinds of different things happening on it. So as we can make our models higher and higher fidelity, we can improve the quality of that science. And by improving the processes that we calculate, so more and more work on the different cycles, water cycle, carbon cycle, nitrogen cycle, and so forth, we get better and better science. There are some challenges when we apply AI to this. I'm sure most of you are aware of the fact that things like some of the large language models like ChatGPT have a tendency to occasionally hallucinate. And the general idea with neural networks is that they'll always give you an answer, even if they have no idea what the answer should be. And that can be challenging. So we need to build guardrails into our models to ensure that what we're doing is scientifically valid. Neural networks in general are very good at interpolating data. They're very poor at extrapolating data. And the problem with climate change is we have an uncertain future. And so our models need to understand that we can't just rely on 40 years of what happened in the past to predict what's going to happen in the future. So yeah, there's a lot of work that goes into that. But also you'll notice with the reports that we put out through the United Nations, like the IPCC reports, we use a lot of very flowery techniques to say things like, this is maybe, we're trying to give likeliness on every statement that we make. This is highly likely, or this is possibly likely, or this is slightly unlikely. The wording is deliberately vague for the reason that we can't have 100% confidence in anything, really.
Okay, thanks, Jeff, for your presentation, and much appreciated for your this joining us today. So maybe if we can give a round of applause for